Okay, so in this lecture, I want to look at the chemistry of the functional group that we were introduced to last time, which was the alpha beta unsaturated carbonyl. So the unsaturated alpha beta unsaturated carbonyl, recall, is a functional group where we have a carbonyl, and then at the alpha position extending into the beta position, we have an alkene. This is not one where we do something like this. It turns out that that is a poorly drawn ketene for later. Don't worry about it. Or we could have the non-conjugated version, but neither of those are what we're looking for. Okay, rather, it is this structure here. Okay, so what I want to do is, first of all, recognize that in the alpha beta unsaturated carbonyl, the alkene is in conjugation with the carbonyl. So the alkene is in conjugation with the carbonyl. Now that's important to note because that's going to affect what the resonance structures are that we draw this thing. Speaking of that, let's draw the resonance structures of an alpha beta unsaturated carbonyl. Okay, to do that, what we do is we start with our best resonance structure, which is the neutral form. All the charges are accounted for. Everything's kind of taken care of. And we draw some resonance structures where let's first of all lift the carbonyl oxygen, the carbonyl pi bond up and onto the oxygen atom, putting a negative charge at the carbonyl oxygen and a positive charge at the carbonyl carbon. Now, if you look, we have this system. We've seen this before. This is an allylic cation, sort of. It's an alpha beta unsaturated carbonyl resonance structure. Okay, it's got some other stuff going on, but it kind of looks like an allyl where we could swing the double bond over, neutralize the positive charge, in this case on the left, and give a positive charge now on the right. Now, it's this resonance structure on the furthest to the right that I think is most helpful. Okay, it's not the best. The best one is probably, or is definitely the first one. But this one tells us that the beta position is reactive. Now that's really kind of the big take-home message here, is the beta position is reactive. So in alpha beta unsaturated carbonyls, help if I spelled it correctly. So in these systems, both of the carbonyl carbon and the beta carbon have positive character. Okay, so if we look at this, what I'm saying is that if we highlight this position, that's the carbonyl carbon. That has positive character according to that resonance structure. The beta position has positive character according to that resonance structure. So both of these now have an opportunity to react with a nucleophile. So what does that look like? Okay, let's say a nucleophile adds to the carbonyl carbon. And we follow it with H plus workup. All right, so what we're going to do here is just consider the resonance structure where the electrons are boosted onto the oxygen, but the positive charge hasn't moved according to the allyl resonance structure. Okay, in this case now, the nucleophile is going to add to this position to give a product that looks like this, which can be neutralized by the H plus in the following step. Okay. As a shorthand, this type of addition is typically called 1,2 addition. Because in this case, the H plus and nucleophile added to the first two atoms. So they added to the first two atoms. We have kind of atom 1 and kind of 2. We added the nucleophile to the atom 2 and the hydrogen to atom 1. Now, what am I talking about? What is this numbering scheme? Well, let's look at it this way. Here is my alpha beta unsaturated carbonyl, and we said that it has positive character at the carbonyl carbon and the beta carbon. Let's number these things from 1 all the way to the end of this particular functional group, which has 4 atoms in total. I'm going to start at the 1 at the oxygen because it's the most, it's the heaviest element. Let's give it the highest priority. Typical things we do as organic chemists. So adding the nucleophile to the 2 position and the H at the 1 position is called 1,2 addition. So in 1,2 addition, the H plus and nucleophile minus go to the 1 and 2 atoms. And based on my listing, they go respectively. Now there's a different form of addition called 1,4 addition, and this is often called conjugate addition. Now to keep that in line with what I just said, in 1,4 addition, the H plus and nuc add to the 1 and 4 atoms. Now, why would they do that? Well, this is called conjugate addition. Called conjugate addition because this takes advantage of conjugation or of the conjugated alkene. Okay. Now we said that there was positive charge character at the carbonyl carbon and the beta carbon. In 1,2 addition, the nucleophile adds to the carbonyl carbon or the second atom. In 1,4 addition or conjugate addition, we're going to see the nucleophile add to the 4 position. Now, why would it do that? Well, let's go ahead and go back to our resonance structures. Let me go ahead and get these numbers in front of us again. So we could boost the electrons onto the oxygen, and then we could swing the electrons over. And in this case, for this resonance structure, we could go nucleophile here, and then H plus here. Whoop, I'm going to have I'm not going to break the rules. There we go. Negative adds to positive. Okay, so the H plus goes in the oxygen still, and the nucleophile goes at carbon 4. That's called conjugate addition, and that leads us to a new reaction called the Michael reaction. So the Michael reaction involves the conjugate, I like conjugate addition, but 1,4 addition is also good because that helps remind us that 1,2 addition is real. So the conjugate or 1,4 addition of a nucleophile to an alpha beta unsaturated carbonyl with an enolate intermediate. This is a cool reaction. This is a super useful reaction. Okay, so what you can do is you could take a carbonyl and add a nucleophile to it. And this works really well for some particular classes of nucleophiles. You can add a nucleophile to it, and you get this structure here. If we have a nucleophile minus and we have a then H plus, you might be like, wait, up above we had the H plus adding to the oxygen. That's how we get the 1 in the 4 addition. Now we've just got like a 4 addition, and I don't know what happened to the H plus. It turns out the H plus is here. Why is the H plus there? Well, the H plus is there due to tautomerization or enolate protonation. All right, let's go through the mechanism. So the mechanism looks like this. I'm first of all going to consider resonance structures where we push the double bond over, the carbon-carbon double bond over, and the carbon-oxygen double bond up to give us a resonance structure in one fell swoop with 2 arrows, where we have a positive charge at the beta position, positive charge at the 4 position. Now we're going to add our nucleophile to this position to give us a new structure. Now it's important to note that this structure that we get is, first of all, missing a carbon. Oh my goodness. This is the hardest part about these Michael additions, is because of bond line structures, you're going to forget your carbons. Okay, 1, 2, 3, 4. Okay, new bond goes to 5. There's our nucleophile added with our new bond in blue. Okay, so now up here, what I want to point out is that we have an enolate across 1, 2, and 3. So when we add our H plus, a few things can happen, and you can draw them any way you want. But in step 2, we have our H plus. Okay, the negative charge could reach out and grab the H plus. I'm fine with that. I'm fine if you do that. You just have to recognize that at the end of this, we're going to see an enol, which will tautomerize, and you don't have to push the arrows at this point for the tautomerization reaction. But you just have to recognize that that enol is going to want to be in its keto form. I guess this is an aldol form, isn't it? The enol is going to want to be in its aldol form by tautomerization. Now, alternatively, and I like protonating the oxygen and doing the tautomerization, but if you say to me, nah, I got this, I'm going negative charge down, double bond over to pick up the H plus, where the H plus is now delivered directly to the alpha position. That bypasses the enol intermediate completely and goes right to the keto form, so you don't have to worry about tautomerization. That's fine with me too. But that's the Michael addition. We add to an alpha-beta unsaturated carbonyl at the beta position. It's a conjugate addition reaction. It's a 1,4 addition. It's the first part of a 1,4 addition, and we involve an enolate intermediate, which then gives rise to a ketone form or an aldehyde after a hydrogen transfer at the end with workup or picking it up from a substrate. Now, some of these things work so well they don't even need the H plus workup. A great example is the addition of thiols to alpha beta unsaturated carbonyls. So thiols, these are sulfur versions of alcohols, so RSH. So if we did the following reaction, there, ethane thiol, that's that molecule I was telling you about that stunk up the whole building when I was in grad school. Made some enemies that day. Okay, anyway, we don't even have to add any reagents to this reaction. It will spontaneously add sulfur because sulfur is a good nucleophile, and the hydrogen that we don't have to draw goes right here at the alpha position. But this is a Michael reaction. Okay, there's a few ways to look at this. What I'm going to do for my mechanism is consider the charge-separated species where I have negative on the oxygen, positive at the beta carbon, and that's going to adduct with this thiol that could exist in a deprotonated state, or it could add as a neutral structure. It just turns out that it's probably neutral, but I think this is helpful for seeing what we're working with here. It turns out that sulfur on its own, whether it's negative or neutral, is very nucleophilic. It's also very acidic, which is kind of why I'm okay with some small concentration of the thiolate, the sulfur with a negative charge. Others probably don't like it. Okay, anyway, negative is attracted to positive. And sulfur, being just down a row in the periodic table, highly polarizable element, very nucleophilic, provides a large opportunity to donate electron density into electrophiles. Okay, so there is our enolate species, which then adds to H plus and goes right to product. Okay, so we're taking advantage of the fact that sulfur sulfur is a good nucleophile, and it can add to that carbon that's a good beta the beta position of our carbonyl. Let's see, let me get that on screen for you. Okay, another example, cyanide also works. Cyanide also works, where cyanide is Cn minus, negative on carbon. So we could do the same reaction. I'm going to pick this example because this example points out the fact that we have to ignore beta carbons on aromatic rings. Why do we ignore those? Well, if we add there, we're going to lose aromaticity, and the molecule is not going to like it. So we're not, the beta positions that are within benzene rings cannot participate in the reaction. So we have to use the one that's not within the benzene ring, which is on the right. So I'm going to show that resonance structure. And I'm going to add to that Cn minus. Okay, now let's be careful about our carbon count here. This is the part of the semester when everybody starts losing carbons. All right, there's my structure. There's my new bond. 1, 2, 3, 4. Now, triple bond N. You can see with that triple bond in there, it's pretty easy to draw something like that where you lose a carbon atom, right? Okay, so that's the correct species, and then with H plus workup. And then add H plus to the alpha position and give rise to our neutral carbonyl. It's a really cool reaction because you can just add so many nucleophiles and make so many interesting bonds, and at the end of the day, you still have your carbonyl to do all the stuff that carbonyls can do. I don't know. I think it's fun, but you know, I live in this world. Okay. Let's do another cool example before we get into some, I mean, still cool examples, but some organometallic things. So it turns out that Malinate esters can also add, and these fall into a class of 1,3-dicarbonyls. 1,3-dicarbonyls are systems where we've got hydrogen atoms that are alpha to 2 carbonyls. These are now very acidic. So 2 carbonyls are surrounding those hydrogens, so they're both pretty acidic. Now, as a result, what we can do is readily form the anion. Now, I like to pick malanates. So malanates are when the R groups are O something, and we have an ester. It turns out it's an ester of the 3-carbon dicarboxylic acid malonic acid. We won't worry about that right now. So in that case, what we have is an OR group. These work really well because we've only got alpha hydrogens between the two groups. So these are the only alpha hydrogens. Okay. So what we can do with this is I'm going to keep the alpha beta unsaturated carbonyl. But these can react with base and add to alpha beta unsaturated carbonyls. All right, so it looks like this. We have our malanates with only 2 alpha hydrogens between the 2 carbonyls reacting with a very mild base. Sodium hydroxide is generally, or potassium hydroxide, generally pretty capable about this. That negative charge is just so stable. The more we stabilize that negative charge, the stronger the acid is. So we now have a negative charge, look at that, between 2 carbonyls, definitely something that's not hard to make. Now it's this position that is our nucleophile. So I'm going to do is I'm going to consider the simplest alpha beta unsaturated carbonyl. I'm going to mix that with RO carbonyl, C the negative, carbonyl OR, and this is going to add to that positive character at the beta position. Negative attached to positive. Now this is the challenge of bond line structures. Okay. Negative. Enolate. Beta position. The privilege of being able to draw on an iPad so you can draw blue lines for your new bonds. Now the rest of the Malinate core. Alpha to 2 carbonyls with OR groups. Okay, there's the structure. Now we add some H plus, which reacts with the enolate, and we're probably good enough to just neutralize this from the H plus that can be pulled off of the next malinate to do a reaction. So this also works exceptionally well. And if you look at this, yes, it's a super cumbersome molecule to draw, but I'm telling you, at the end of the class, the harder these bond line structures are to draw, it's just kind of an artifact of, like, not losing track of carbon atoms. The harder they are to draw, the more important the molecules are that you're making. I mean, look at, we're making carbon-carbon bonds in almost every case now of the reactions that we're looking at. This is such powerful chemistry and is used so much. The aldol reaction, by far one of the most often used reactions to generate molecular complexity within biology, and it's used all the time in medicine. Michael reaction is up there too, just by the sheer volume of alpha beta unsaturated carbonyls that are out there because of the aldol condensation reaction. Okay, we need to talk about a dilemma though, and that is the addition of R minus, which is a carbanion, from organometallics. Okay, so we've had a lot of fun thinking about the nucleophiles that can add to our beta position of our alpha beta unsaturated carbonyl. And the Grignard reagent is one of our favorite nucleophiles, right? So let's go ahead and add that. Here's the issue. If I take my alpha beta unsaturated carbonyl, consider a resonance structure of it that shows the positive character at the beta position. Both of these structures are good, right? And in fact, there's this structure down here that I've sort of ignored because I've been picking on really good substrates for conjugate addition. But if all of these represent the same molecule, if I add an RMGBr followed by H plus, the outcome that I get is my product from a Michael reaction, which is going to be the 1,4 addition product. Remember, the 1 goes on the oxygen, tautomerizes over to the alpha position. But I'm also going to get a competitive amount of my 1,2 addition. And you get a mixture. So a mixture of 1,4 and 1,2 addition products form when Grignard reagents are used. When Grignards are used. Oh, sad face. Okay, so what are we going to do? Well, we can turn to some different organometallics, and it turns out we can use organolithiums, where instead of R being attached to MgBr, we can attach that to lithium. So R lithium is equivalent to R minus, really, if you cross out the lithium, just like we do for Grignard reagents all the time. So if we do that reaction, we follow it with H plus, it turns out we almost exclusively get 1,2 addition products. Huh. Well, the conjugate addition was so useful. It would be great if we had some way to get those products. It'd be great if we had some way to get the conjugate addition products. Okay, well, how do we do this? It turns out that we invented a new class of reagents called Gilman reagents to kind of take the place of Grignard reagents just for this purpose. Along comes Gilman reagents. And in Gilman reagents, these are pretty funky, but they're actually made from the organolithiums, but they're pretty funky. What it is it's R, Cu, R, negative on the Cu, countered by a lithium plus. And these are often written as lithium CuR2. Now, this isn't a transition metal class, so the copper really kind of screws up our intuition quite a bit, but these are dialkyl lithium cuprates or Gilman reagents. And what I want you to think about them as is they are R minuses that add to the beta position. This is the problem I wanted to solve. I wanted to do conjugate addition only. I wanted to do addition to the beta carbon and alpha beta unsaturated carbonyls. This is the answer, okay? That is, if I take this and I react it with R2CuLi, drawn in all of those ways, or lithium CuR2, or RCuR lithium, all these ways. I just want you to see all of these and say, okay, I've got my R minus, and this R minus is now poised for a number of kind of metallo reasons for the R minus to add to the beta position. They figured it out, okay? Well, that's great. That really expands the utility of the Michael reaction. And so copper just in general favors addition to carbon-carbon pi bonds over carbon-oxygen pi bonds, and we get this species, which we can then follow with H plus to give us this molecule here. Okay, and that's the extent of the mechanism I'd want to know. I'd want you to know. Instead, we could look at some examples of this. Let's say we've got, I'm going to do 2 examples. I feel like I've defined phenyl pH, but let's go ahead and just draw some benzene rings here. Okay, we'll assume when we need it, we've got the H plus. Nothing fishy there. Alternatively, this is another favorite example of mine. Let's draw the condensed version so you can see what that looks like. Okay. Okay, so the answer, let you pause if you want to try to solve these. Otherwise, I'll go through the answers right about now. Okay, so we just kind of consider the resonance structure of these. I'm going to go over so I don't kind of confuse the issue too much. Negative on the oxygen, positive at the delta carbon. Down here, we're going to ignore the beta position in the benzene ring and focus only on the beta position outside of the benzene ring. Okay, so now what I want you to think about this as is a phenyl minus or a benzene minus. Remember, pH is short for phenyl, which is a benzene substituent. Here, the negative is going to add to the positive. Then H plus is going to give rise to this species. Now, alternatively, we have an ethyl group being added. These short chain alkanes can be kind of a bear to attach to the chain. So there's my beta position, 1, 2 carbons from the ethyl group. If I wanted to make sure I didn't lose any points, I'd probably, and I was in a rush, there's my carbon framework from my alpha beta unsaturated carbonyl. I'm going to bond that to ethyl, where I've got my new bond drawn here. It's a little bit easier to see, harder to see down there. Okay. All right, that's what I want to cover in terms of pure alpha beta unsaturated chemistry. There's more reactions we can do with these really powerful functional group. Not quite the carbonyl, but awesome because anytime we can have a carbon atom that's active and can react with things, it's exciting. Okay, well, that was lengthy enough. Let's go ahead and stop there.